In this video, we'll discuss the concept of electrical power and show how it applies to resistors. Now, the basic idea of electrical power is that we're going to convert electrical potential energy into some other type of energy at a certain rate. And power in generally is just the rate at which energy is converted, or in general just a rate of energy change. But in this case, we'll specifically mean from electrical potential energy into something else. Now, the formula for it, which is universal formula, is that the power is the current times the voltage drop. We mean that there is a certain number of electrons that pass through that material every second. That's what the current is measuring, how much charge there is passing through that material every second, times how much energy each charge loses as it passes through there. And since we're talking about the number of charges per second times the energy loss per charge, you put that together, you just get the amount of energy per second. And that's really what the power is. So for any circuit element, if you multiply the current through it times the voltage drop across it, that tells you the rate at which it is converting electrical potential energy into some other form of energy, or perhaps storing it up in some way. In the case of resistor, we're taking electrical potential energy and turning it into internal energy, in this sort of a thermal energy, the energy that's going to then heat up to a higher temperature. So there are three different equations you can use to find the power. You can use the original, P equals I delta V, or you can use the two other ones, I squared R or delta V squared over R, because the resistance is related to the current and the voltage drop. So we have three variables to talk about: current, voltage drop, and resistance. But you only need to know two of them to find the third. And again, we'll use Ohm's law, which is this equation, delta V equals IR, and then either solve for delta V or solve for I, and then plug it into the delta V equals, the power equals the current times the voltage drop equation, leading to either I squared R or delta V over R. Now, when you use these, you want to think about which quantities do you actually know. Let's give an example. Say I want to plug something into the wall. Walls provide a certain voltage drop, not a certain current. It has a fixed amount of voltage difference between one prong and the other prong. If I plug in something with a very small resistance and I want to find the power, I'm going to use the right-handmost expression, because I don't know what the current is. I don't know if the current is increasing, decreasing, or staying the same. All I know is that the voltage drop is the same, and I know something about the resistance. And this would tell me that if I put in different objects that would have less and less resistance into a socket, I would have more and more power loss through them. So if I plug in something like a wire, which has a very, very small resistance, it'll have a very, very large power loss, which means that the electrical potential energy is going to be converted into thermal energy very, very quickly. And that implies that the wire would heat up very hot and could potentially melt or burn you. So this effect is called shorting something out, whereby sticking something that has a very small resistance into something with a voltage drop, you end up having the current get diverted around it so that all of the energy loss, or all the power, is deposited in the wire rather than in the circuit element. And if you short out a power supply, like a plug in the wall or a battery, you can often cause burns to yourself because you'll heat up the wire so hot, or melt something, or catch something on fire due to the excess heat.